Greetings and welcome to the Chemistry 150 Problem Solving Lab. This lab is arguably one of the most important labs because it really invokes the skills that you're going to need all the way through your chemistry career. And even if you are only taking this class and you won't be taking the other ones, it will still help you because you'll go to the store and you'll need to do some kind of weird conversion, and all of these things and stuff are going to be really helpful to you. So just realize that these are kind of the things that allow you to get into the cooler parts of chemistry and see what's going on. Problem solving is a big part of not just chemistry, but all science, all right? And of course, science started because we were trying to make rationale as to why the world worked. And that's kind of what we're going to be introducing here is some of the skills that people use to figure out how things work. And the skills we're going to look at specifically in this lab include the scientific notation, which is a way to express large and small numbers easily and in a compact fashion without counting a gazillion zeros, which drives me crazy, but that's another story. The metric system, which you may already be familiar with, but the metric system is integral in chemistry and science. It's all based on powers of 10, so we'll talk about that a little bit. There's something called dimensional analysis, which is how you convert one type of unit to the other. And also we're going to look a little bit at significant figures, which is how chemists make sense of the data we have and try and keep it consistent so it makes sense from one scientist to the other. And again, if you can conquer these, you've really got all the skills you need to do well in chemistry, all right? There'll still be some work, but you'll have the foundation for making these kind of things happen. So let's start off in talking about scientific notation. In the day-to-day world, all right, where you deal with numbers, say, that are, usually greater than 0 and maybe less than 10,000 or something like that, you can write them all out like normal. But in chemistry especially, and a lot of the sciences, we deal with numbers which are just massive, huge, all right? Like numbers we'll talk about in lecture that are just so big. But we also talk about numbers that are super small. So like the distance between atoms, for example, is something that's very small compared to our day-to-day world. So scientific notation just allows us to express both of these. So let's say that we have a number that we wish to express in scientific notation. We always, when we convert to scientific notation, we write it as a number between 1 and 9, and you can have a decimal and all the other numbers go beyond it, all right? And that number between 1 and 9 is multiplied by 10 raised to a power. And the power will tell us how many places we've moved that decimal point, and I'll show an example of that here in a little bit. Now, one thing that helps is that a 10 to the 0 in math is just equal to 1. So if you multiply something by 10 to the 0, it's like multiplying by 1, and that's no big deal. If you move the decimal point to the left, it's going to increase the value of the exponent by 1. And if you move the decimal point to the right, it's going to reduce the decimal by 1. And I'll show examples of that because I know that's kind of weird. Here's two examples. Here's a big number, all right, this 0.000012. And that would be a number that would be pretty annoying. And we can write that, though, as 0.0000 whatever 12 times 10 to the 0, which is 1. But notice that if you want to have a number between 1 and 9, we have to move that decimal point over, we need to move it over 1, 2, 3, 4, 5, 6, and we're moving it to the right. So in order to express this new number as 1.2, there's the part between 1 and 9, as 1.2, and we moved it to the right 6 times, we reduce that 10 to the 0 6 points. So this new number is 1.2 times 10 to the minus 6. And notice here how this number, which is much less than 1, has a 10 to the minus 6. And that doesn't mean it's a negative number. It just means that it's a very small number in scientific notation. And that's kind of important. Now, if you have a large number like 215, you can see what's happening. You initially write it as 215 times 10 to the 0, which is kind of boring. But here's the punchline. To make it a 2.15, we need to move that decimal point over 2 spots, so it becomes 2.15. And because we went left, it's a positive positive exponent. So 215 would be 2.15 times 10 to the second. This is how you take big numbers and small numbers and turn them into scientific notation. And it's not too hard once you get used to it, like anything, right? Anyway. Sometimes you want to take scientific notation and convert it back to a regular number format, and that's no problem too. You just move that decimal point, same number of places as the value in the exponent, and eliminate the exponent part of the number. Because remember, times 10 to the 0 is just 1, and you don't really have to show that unless you want to. And again, like before, if the exponent is a positive number, that means you've got a number that's greater than 1, so it's going to be big. You'll move your decimal to the right. And if the exponent is negative, like that 10 to the minus 6 number we saw, you'll move it to the left, and your number should be quite less than 1. So again, remember, if you have times 10 to the third, that's a big number, and times 10 to the minus third would be a number less than 1. So here's some examples. 1.23 times 10 to the 6. We would move that 10 to the 6, we'd move that decimal over 6 times. So 1, 2, 3, 4, 5, 6. I'll pretend there's zeros there. Here's what the number looks like. 1,230,000 would be that number. And here's an example of taking a small number and converting it over. And you can see that 10 to the minus 8 means that you move that decimal over 8 spots. So you've got 0.000000156, pretty chill. Now, your calculator should be able to do this for you automatically, and every calculator is different. There's usually some kind of a function where it's scientific or normal or regular. It's got different names. But one thing I would do in this lab is make sure that you know how your calculator can be converted to scientific notation and back again, and it will save you a lot of time. It's really frustrating to read a lot of zeros when the number is smaller or greater than 1 by quite a bit. Scientific notation and your calculator will do that for you, and I highly, highly, highly encourage that you check that out. Now, the metric system is our second thing, and some of you are familiar with this, and you're welcome to skip through it. You don't have to watch this video like a Hollywood video or anything like that. But if you are new to the metric system is based on a bunch of abbreviations, and they all have a numerical value associated with them. And some of them that you're probably familiar with, kilo, which is used for like kilometers and stuff like that. You might have heard of a centimeter, which is centa, all right? Kilo is always 10 to the third, or 1,000, all right, in scientific notation. And centa is always 10 to the minus 2, or 0.01, and that's going to be really handy. Now, in chemistry, we deal a lot with kilo, centa, milli, micro, and nano. So just realize those 5 are going to show up a lot. And there's more even than on this list, but do realize that those 5 are going to have a lot of interactions with, so make sure you've got them ready to rock. Each one of those metric prefixes you can use in different contexts depending on what you're measuring. So for example, if you were at a sporting event, you may want to be measuring length. Length is like meters, so they'll talk about kilometers being measured. Or if you're measuring pieces for a model airplane, I don't know, maybe you deal with centimeters. But notice that all of these, the base unit they call is the unit of length, which is the meter. On the other hand, in chemistry, a lot of times we will measure things in kilograms, which is a bigger amount of mass, sometimes in milligrams or centigrams. So notice how we just changed the base unit. Instead of measuring length, we're measuring mass, how much mass an object has. No problem. All these conversions are going to work. Now, this works for other things too. Volume is one of them. So for example, if you go to the store and you buy a soft drink, it's probably going to be measured in, I don't know, maybe a liter or something like that. You can also have milliliters, which is very common. You'll see that on a lot of the containers. A kiloliter is used once in a while. And you can do this for time. So here's ones for millisecond, nanoseconds, kiloseconds, and there's lots of different kind of base units you can use. So all these metric prefixes will work. Their relative amounts are the same. You just change the base unit depending on what you're measuring. the relationships between the metrics are really important. And here's some examples for length, which is something we'll use quite a bit. Here's a relationship between a kilometer and a meter. And remember earlier we saw that kilo was 10 to the third, and 10 to the third in scientific notation is 1,000. So that means there's 1,000 meters in a kilometer, all right? And there's decimeter, which is used a lot. So there's 0.1 meters in a decimeter. Honestly, that's not used very much, but it's a good example. Centimeters are certainly used. 0.01 was the metric prefix for centa. So that means 0.01 meters per centimeter. And notice again how that metric number that's associated with it, that goes in front of the base unit, and then the centimeter equals 10 to the minus 2 meters. And that's kind of cool. Now, 10 to the minus 2, if you place it on the other side of the equation, becomes 100. So a lot of times you'll see that 100 centimeters equals 1 meter. That is equivalent to saying that 0.01 meters equals 1 centimeter. It's kind of a cool math trick. And if you keep going, the milli was 10 to the minus 3. So that means there's 10 to the minus 3, or 0.001 meters per millimeter. But again, like with centa, you put the 10 to the minus 3 on the other side. 1,000 millimeters also equals a meter. So there's more than one way to do these kind of problems. There's also milligrams, milliliters, and the same kind of thing. We're just changing that base unit. I want to put it out. So if you're measuring mass, grams, instead of length, meters, you could also say that a milligram is 0.001 grams, or 1,000 milligrams is a gram. And a milliliter, which is in volume and on lots of soft drinks, a milliliter, 0.001 liters, or 1,000 milliliters per liter. Down here I have a thing. A milliliter and a centimeter cubed are the same, and we'll talk about that in lecture more. Sometimes you see centimeters cubed as cc, especially in medicine, all the same thing. We also in chemistry deal a lot with micro and nano, so I'm just putting them out here. Micro is 10 to the minus 6, so a microgram is 10 to the minus 6 grams. And if you put 10 to the minus 6 on the other side, that's a million. So there's a million micrograms per 1 gram. And a nanogram is 10 to the minus 9. So when you convert that over, 10 to the minus 9 on the other side becomes 10 to the positive 9, which is a billion. A billion nanograms is 1 gram. So you're seeing here that there's lots of different kinds of units that are used in chemistry, but we can convert them. So mass would be grams, volume would be liters, length would be meters, and that kind of stuff. Dimensional analysis is what allows us to convert one kind of unit into the other. So let's talk here a little bit about the numbers we're going to see in chemistry. So 5.2 centimeters is a number you might see. And 5.2 tells us how much, if you will. And the centimeter tells you what it is. So in this case, it's a length. Meters is length. So you have 5.2 centimeters. 16.237 grams, the 16.237 is how much. And of course, the gram tells you have some kind of mass. So both the number and the unit, super important in chemistry. A lot of times you want to convert, though, like centimeters to kilometers or grams to nanograms, something like that. And so what people use is something called the factor label method, or what we a lot of times call dimensional analysis. And all that really means is that you're trying to convert one type of species into another, or one type of unit into another. And you do this a lot day to day. You just don't think about it. All of these things have to have conversion factors. So it allows you to go from one type of unit to the other. And if all of that makes as much sense as me speaking a different language, I completely understand. Let's look at some examples. Here's some examples of conversion factors you're probably used to. All right. So for example, good old Oregon, I grew up with the English system. 12 inches is equal to 1 foot of length. All right. And in chemistry, I probably wouldn't use this, but here I can talk talk about it. That's pretty common. If it's a conversion factor, you can write it as 12 inches per 1 foot, or you can flip it because 1 foot is also equal to 12 inches. So the first thing I want to let you know is that any kind of conversion factor you're going to see, it's basically just a fraction, and you can convert it, flip it, all right, as you need. Now here's one I use several times: 4 quarters per dollar, and of course you can write that as $1 for every 4 quarters. So if you started with dollars and you want to know how many quarters you had, you would use the first one. So for example, $2 times 4 quarters per $1 would be 8 quarters. All right, no big deal. On the other hand, if you had 8 quarters and you want to know how many dollars you had, then you'd use this one. 8 quarters times $1 per 4 quarters would be $2. So see how you automatically use these sometimes and you don't even think about it. Here's the length conversion. If you want to convert kilometers to miles, 1 kilometer is 0.6214 miles, and you can write it either way. We're going to see lots of types of conversion factors in chemistry, and just remember, they're just like fractions, and you can flip them as you need them. The goal here is going to be to make the old unit cancel and the new unit come out, and so that's why you can flip them either way. As long as it's a conversion factor, that's not a problem. You want the unwanted units to cancel, which is usually the starting unit, all right? So here's an example. If we wanted to know how many kilometers are in 26.22 miles, the unwanted unit, if you will, is the mile, and the wanted or desired ending unit is kilometers. So we can use that previous example of 1 kilometer equals 0.6214 miles to get rid of the miles. We don't want the miles anymore. Now in math, miles over miles is like 3 divided by 3 or x divided by x. They cancel out. And the same thing applies to miles. So the miles here are canceled out. Kilometers is the only unit left standing, the only one that's still there. It's in the top, which is what we want. So to convert miles to kilometers, you take 26.22, divide 0.6214, put that in your calculator. I'm going to call it 42.20 kilometers, and I'll talk to you why. This is the answer that I actually got in my calculator. Well, that's a sig fig thing. We'll talk about that in a little bit. But the important part now is that all this dimensional analysis stuff, it's just about converting what you're starting with into what you want. And you need conversion factors along the way. And all these conversion factors can be flipped. So the top can go on the bottom and the bottom on the top, or you can use it as is. Either way, it becomes easier once you see it. Here's an example. Let's say we want to know how many hours there are in 3.5 weeks, okay? So in this kind of problem, which you could probably do yourself, you're starting with weeks and you're going to hours. You want to know how many hours are in there. And along the way, you're going to need a conversion factor or maybe more than one conversion factor to do it. So what I did when I solved this problem is, okay, we're starting with weeks, all right? I want to get to hours. Now, there's probably a way to figure out exactly how many hours are in a week, but I don't know what it is. So I'm going to use the ones I do know. 1 week is 7 days, and 1 day is 24 hours, at least unless you're a hyper astronomer, which is a different story that we don't need to talk about here. But anyway, let's assume those are exact things. So I can go weeks to week, and those will cancel out, and I'll have days. And days and this day I can cancel out to get just hours. And I'll show you what that means here. So if you put these things in a row, we want to start with 3.5 weeks. Then to get rid of weeks, we're going to put the 1 week on the bottom and have 7 days on the top. That'll cancel the weeks, and then I'll have days. But I want to get to hours. So then I'm going to put 1 day on the bottom, 24 hours on the top. The days will cancel, and we'll have just hours. So this is what I did right here. I'm starting with 3.5 weeks, 7 days divided by 1 week. This week is on the top, this week is on the bottom. If I was to stop right there, that would give me how many days are in 3.5 weeks. But again, the idea is we want to get to hours. So I'm going to put 1 day on the bottom and 24 hours on the top. And if I do that, the day on the bottom here cancels the day on the top right there. So mathematically, go 3.5 times 7 times 24. Your calculator will tell you 588. I'm going to call it 590 due to significant figures, which we'll talk about in a little bit. But this is how you convert one type of unit into the other. In this case, it's weeks into hours. And again, you might have multiple conversion factors. You might have just one. But the idea, cancel out the old unit and end up with only the unit you want at the end. Here's another example. How many centimeters are in 4.7 kilometers? Okay, so kilometers is our starting unit, and we want to end up with centimeters. So when we do this problem, we're going to need some way to convert kilometers into centimeters. Now again, there are ways to go directly from kilometers to centimeters, but I don't know what it is off the top of my head. 1 kilometer is 10 to the 3 meters. We saw that kilo was 10 to the third, so that's where I'm getting this, and I'm putting the base unit of the meters. Here's also a centa was 10 to the minus 2, so a centimeter is 10 to the minus 2 meters. So in this problem, I'm going to use the 4.7 kilometers, and I'm going to cancel it with this kilometer to get meters. And then I can use this meters and that meters to cancel each other out and be left with just centimeters. So what I would do here, start with 4.7 kilometers times 10 to the third meters per 1 kilometer. This kilometer on the top and bottom cancel out, so we have just meters left over. But again, we want centimeters. So then I'll put 10 to the minus 2 meters on the bottom and 1 centimeter on the top. Meters cancel out. I've got just centimeters. 4.7 times 10 to the 5th centimeters is the final answer. So this is how this works. And all the problems we're going to do in chemistry are like this, all right? You're starting with one thing. You want to convert it to something else. You need more, sometimes one, sometimes more than one conversion factor. This is how you get to the final answer. Now, significant figures is the last thing I want to talk about real fast, and this is also really important. So let's say that you had this graduated cylinder with water that we see in the picture, and you want to tell me how much water is in there, all right? Well, 15 milliliters is here, and 20 milliliters is there. So 15, 16, this number right here would be 17, and this number would be 18. So I think we can all say that it's at least 17 and less than 18 milliliters. That part's no problem. But do you go farther? Like, it's not exactly 17 milliliters. It's kind of halfway, maybe 17.5. But you might look at it and go, well, I don't know, it looks more like 17.4, 17.6. And welcome to the real world of science, because every measurement you have is going to have a degree of uncertainty. And what that means is that every person, or machine for that matter, that looks at a type of a measurement is going to have a little bit of uncertainty. And the question is, how do you record this? Because everybody's going to have a slightly different value. So the question with sig figs is, how do you make this recording? Like, what do you call it? 17.5, 17.4, 17.55? I mean, do you just round it off to 17? What do you do? And that's the real question. So sig figs, which is the abbreviation for significant figures, huge part of chemistry. And that's what we're going to talk about. Now, as the chemistry instructor, I take off more points for sig figs than anything else. So if you spend the time and really go through these sig fig rules, you're going to do really well. It's kind of not the most exciting topic in the world, but man, is it important. So if you can do it, I sure encourage you to hit these rules pretty hard. If you have a number, all right, there's going to be some numbers that you know very well and some which are uncertain. So in chemistry, we always call the last digit the doubtful digit. It's the uncertain one, and that's the plus or minus. And what that means is that everyone that looks at it, and this includes machines, are going to give you a slightly different final number. So there's a little bit of uncertainty, plus or minus 1 or so. It depends on the thing. Statisticians go crazy on these kind of things. All we're going to know is that that last digit is not known very well. So on these kind of problems then, if you have a number like 65.07, all right, we have to know how many significant figures there are, numbers we have some confidence in, but we also want to know which one is the uncertain or doubtful digit. So a number like 65.07 has 4 significant figures to it. There's 4 non-zero numbers that are meaningful. The 0 in the middle counts. We'll talk about that in a little bit. The other thing that's important, though, here is that 7, that last number, the last number is the doubtful digit, and that'll be important to us later. So in this number, there are 4 sig figs, and the 7, the last one, is the doubtful digit, and we'll see what this means in a little bit. Here's some more examples. 54.07 would have 4 sig figs, and that 7, again, is the doubtful digit. So it would be like 54.06 to 54.08, something like that. Here's another number. This number has a lot more sig figs. 1, 2, 3, 4, 5, 6, 7 significant figures. But again, that 8 is the doubtful digit. So you can see the level of precision goes out quite a bit farther in this measurement than it did in the earlier one. So we say arguably the second one was more accurate to a small level, something like that. Zeros are always the tough part. So we're going to go through some super boring rules here, and I apologize, but zeros are the ones that are always difficult to figure out if they're significant or not. So the first one, if you have a 0 between non-zeros, then they count. And that's what happened in that very first example we looked at. So in 69.08, the 0 in the middle does count. It's significant. This would be a 4 sig fig number, and the 8 would be the doubtful digit. If the zeros, though, are at the beginning of a number, then they are not significant, and I would call them placeholders. So 0.0089, the first 3 zeros just tell you where the number starts. There's a big difference between 0.0089 and 8900. All right, one's really small and one's really big. So the initial zeros just tell you where to start on the number line. So 0.0089 has 2 sig figs. The 9 is the doubtful digit. Note that in scientific notation, that would be 8.9 times 10 to the minus 3. Those zeros disappear in scientific notation. That's another way to kind of show here, at least in this example, that the zeros are not significant. They're just placeholders. If the zeros are at the end of the number, you have to make the distinction if they're at the end of the number and after a decimal point or not. If they're after a decimal point, then they're significant. So 2.50 would be 3 sig figs, and the last 0 is the doubtful digit. 25.00 is 4 sig figs, and the hundredths place 0 is the doubtful digit. So zeros after non-zero and after the decimal count. I like to think about this as the chemists are lazy rule. Chemists would write 2.5 unless we had to, and if it's significant, we will write that extra 0, 2.50. So that's one way to help to figure out what exactly is going on here. 2.50, it would be plus or minus 0.01, etc., etc. The zeros, though, that are after a non-zero but before the decimal, they are tougher to know. All right, so here's an example of that. 1,500 kilograms. Probably only the non-zero numbers are meaningful, so that I think that would be a 2 sig fig number. However, sometimes people just don't get around to it or don't think about it, and they do want those zeros to be significant. So you really need to ask whoever's giving you this this data if it's doubtful or not, or if it's significant. As an example of what I mean, 1500 with 2 sig figs would have plus or minus 100. So if 1500 is just, the zeros aren't significant, that would be somewhere between 1400 and 1600, a pretty good plus or minus. On the other hand, if you had 1500 and they're all significant numbers, then it would be plus or minus 1. So you'd have 1499 to 1501, quite different uncertainties. So you kind of need to know. Sometimes as well, you're going to see 1500 with a dot like that. The dot is kind of the unofficial way that shows that those zeros are significant. So if you see 1500 with a dot and it's not from just a period at the end of a sentence or something, probably that means they're significant. But ask around. Those are kind of the uncertain ones. So here's some examples. Let's see how many sig figs these numbers have. And the first one has a 0 in the middle, so they're all significant. That would be 5 sig figs. The second number there, 0.0834, the initial zeros are placeholders. Those do not count. That would be just a 3 sig fig number. The same for the next one. The initial zeros there are just placeholders telling you where you start. But the 0 between the 9 and the 7 was written for a reason. The 0 between the 9 and the 7 is significant. So that would be a 4 sig fig number. The 2, 9, that 0 in the middle, the 9, the 7, and the 7, all significant. Now, the next one has a decimal. It has non-zero numbers before the zeros, and the zeros are after the decimal, so everything counts. Lazy chemists wouldn't include those last 2 zeros unless there was a reason for it. 6 sig figs. Now, the next two are tricky. 23,000 without a dot and 23,000 with a dot. 23,000 without a dot drives me kind of crazy because we don't really know. It could have 2 sig figs if only the 2 and 3 are meaningful. It could also have 5 sig figs, all of them are meaningful, or you could have some combination. So maybe the first 0 counts and the last 2 don't, or the first 2 zeros count and the last 1 don't. I would recommend this person write that number in scientific notation, because scientific notation would unequivocally show how many sig figs they have, but this is nerdy chemist talking. The last one, though, has that little dot right there, and that means all 5 numbers are significant. And if they are, that's a really good call. If you've got zeros in there that are significant, you should use the dot. Once you know how many significant figures you have and you start doing calculations, you need to know how to round numbers off. Now, calculators are going to give you just a gazillion, nice math word, a gazillion numbers sometimes for their answer. But because chemistry is an experimental science, we can't use that many significant figures. So we've got some pretty specific rules for doing math in chemistry based on the number of sig figs in. And the goal is, man, don't lose your sig figs. The large numbers that the calculator will often give you need to be rounded up to a smaller number and use only significant figures. And we'll see how this works. And by the way, there's different rules for multiplying and dividing versus adding and subtracting. Multiplying and dividing, the sig figs you put in have to be expressed as the number comes out, but you want to use the smaller number of significant figures. So here's an example. Let's say that our car drives 278 miles and we use 11.70 gallons of gas, all right? The calculator gives you this number, lots and lots and lots of numbers. However, in the sig fig world, 278, 3 sig figs, and 11.70, where the 0 is after the decimal, that counts, 4 sig figs. When you multiply and divide, use the smaller number of sig figs. So we want to use 3 sig figs, which would be 23.8. We're going to round up here a little bit. But for right now, just realize that 3 sig figs divided by 4 sig figs, you can only count 3 sig figs. If you had 4 sig figs divided by 5 sig figs, then your answer would have 4 sig figs. Always use the smaller. This works for both multiplying and dividing, which is what we do in chemistry most of the time. When you add and subtract, that's where the doubtful digit's going to pop in, and your answer must cut off at the larger doubtful digit. So let's say that we have 3.18 liters of some liquid, water I guess, and we add 0.01315 liters, so a pretty small number. So when you add these together, all right, you get 3.19315, but where do we cut off the sig figs? And the idea is you cut it off at the larger doubtful digit. So 3.18 stops at the hundredths spot, 2 decimals to the right. The other number stops 5 decimal points to the right of the decimal. So 2 decimals is bigger than 5 decimals. So we're going to cut this number off right there. We don't know what those numbers are up there. Maybe they're zeros, maybe they're nines. I mean, who knows, right? But we can't have any confidence in those positions because the uncertainty in 3.18 is too great. So we're going to cut this off at 3.19 liters. So again, when you add or subtract, you cut it off at the larger doubtful digit. You literally cut the number off because you don't have any confidence in the other numbers that are above it. We use adding and subtracting a lot of times in temperature conversion, so just giving you a heads up. If you have a number that needs to be cut off, which is most of the time, you might need to round up. And that first miles per gallon answer, we saw that. If the first digit you're going to drop when you cut it off for sig figs is between 0 and 4, then you just leave it alone. Don't do anything. But if the number the first number you're going to drop is between 5 and 9, then you round that last uncertain number up. Remember, that's the uncertain doubtful digit anyway, so we may not have a lot of confidence. So let's say we have 2.4271 that we need to cut off at 2 sig figs. All right, so that means the 2 and the 4 will count, but the 271 get cut. So we look at the first digit to be cut, which is the 2. Don't look at the 7 or the 1, only look at the 2. 2 is between 0 and 4, so you leave it alone. The answer is 2.4. On the other hand, 4.5816, if we're going to cut that to 2 sig figs, the 4 and the 5 count, 816 gets dropped. Again, only look at that first number, which in this case is 8. 8 is between 5 and 9. So 4.9 will round up by 1 to 4.6 for the final answer. It's pretty easy, but don't forget to do this. This gets something that people forget about, but it can make a big difference when it comes to the answer. So here's another example where we can put a lot of these different pieces together. And let's say we want to know how many quarters a tourist is going to need to travel 555 kilometers. So maybe we're in Canada. But our car gets miles per gallon as the way to record it, 22 miles per gallon. And right now the gas is an amazing $1.37 per gallon. And also 1.61 kilometers equals 1 mile. So we're looking for the number of quarters we're going to need. And the starting unit on this one, believe it or not, is 555 kilometers. We want to turn kilometers into quarters, which is a strange kind of thing, but that's all right. And you can see along the way we're going to need several conversion factors. 1.61 kilometers per mile will help us turn the 555 kilometers into miles. And then if you look through this, 22 miles per gallon will allow us to go from miles into gallons. A gallon apparently costs $1.37 right now, which, okay, cool. That'll allow us to go from gallons to dollars. And then, as we've talked about before, there are 4 quarters in a dollar. So putting all these together, then, we can kind of begin to see how this works out. Our starting quantity, 555 kilometers. 4 quarters per $1, 22 miles per 1 gallon, 1 gallon per $1.37, and 1 mile, 1.61 kilometers. Now, notice here on the right, I put down some notes about exact or sig figs. Sometimes conversions, like 4 quarters per dollar, that's an exact conversion. 4 quarters will always be equal to $1. No question, all right? However, 22 miles per gallon, That's going to be a number which was experimentally created. We needed devices to make it happen. That's a 2 sig fig number. I bet we could have gotten a better number if we would have thought of that. Maybe it was 21.97 miles per gallon or something. Either way, experimentally derived values usually are subject to sig figs. So 22 miles per gallon, definitely 2 sig figs. This number right here, the dollars per gallon, is also sig figs. First of all, you have to realize that measuring the gallon may not be that accurate. A lot of gas stations will say 137.9 which is a weird way that they kind of do math and gas stations, and I don't know. This is an economic question, not a chemistry question. But anyway, it's not exact. That's going to be subject to sig figs. And we saw earlier a different kilometer to mile conversion that had 4 sig figs. Here we're using one with just 3. This one, exact, questionable. All right, that one may or may not be as exact as I'd like, but that one is more exact than the other ones. Anyway, so here's how you do this. Start with kilometers. All right, your starting unit. Kilometers divided by kilometers, we'll cancel that out. So 1 mile divided by 1.61 kilometers will get us to miles. Then a gallon is worth 22 miles. And notice how we kind of flipped that from before, but that's okay. Conversion units can be flipped. Mile on the top cancels miles on the bottom, and now we're in gallons. $1.37 is the cost per gallon of gasoline. Gallon on the bottom there, gallon on the top cancels. And then finally, the dollar bill on the top here is canceled by that dollar bill by the 4 quarters per dollar. So in your calculator, go 555 divide 1.61 divide 22 times 1.37 times 4. And if you did that problem correctly, the calculator comes up with a huge number. But because of the number up here, the miles per gallon, that's going to be a 2 sig fig value. So 85.86674, etc. We want to cut off at 2 sig figs. That would be the 8 and the 5. The first digit is between 5 and 9, so we're going to round up. 86 quarters is going to be needed. So this problem kind of pulls a lot of this stuff together into one piece. And if you can do this kind of problem, please do it. When you put this in your calculator, don't hit enter in between times. So again, if you go 555 divide 1.61 divide 22, etc., you can do this all in one stop. So don't go 555 divided by 161 equals. That's too many pushing of the calculator buttons, all right? Just do it all without hitting enter. Also, you don't have to go 555 divide 1.61 times 22 parentheses. That's too much work, all right? Literally, 555 divide button 1.61 divide button 22 times 1.37 times 4. That'll give you all one stop, the fewest buttons punched on your calculator. I'm trying to save you time, I really am. Anyway, all stuff you can do. That's really it for this lab, all I had to say. Again, if you have questions on anything, please reach out to me. I'm more than happy to help. The Learning Success Center is also available to help you as well. We're going to get these skills down so you can take care of business and conquer chemistry with ease. Good luck.